So this talk is, as you can see, about attacking applications' use of pseudorandom number generators. It's intended mostly for practitioners, for auditors, for security assessors, pen testers. Just, not so much, we're not going to dwell so much on the math or the algorithms. If you want that, it's in our white paper, so please do check out the white paper. We're just going to talk about applying this in practice, in your practice today. So we're going to present this methodology that's centered on our tool, which we're calling Prankster. And this methodology is for identifying the use of, pseudorandom number generators in applications and then attacking that. So first we do need to explain a little bit of our kind of general conceptualization of PRNGs and lay down some terminology just so we can kind of talk sensibly about what we're attacking and what you need to know to perform these attacks. We'll also talk about some of the common PRNGs. We saw some really prevalent, Microsoft, Google, Oracle, etc. PRNGs. Show you how to use the tool, and then of course we'll get on to attacking stuff with Gabriel. So I'm Derek, he's Gabriel. Chris couldn't make it. We're working with Silence, a security product and services company. We do have day jobs there. They keep us very busy, but we do occasionally sneak in some research, and so that's what we're presenting today. So let's get through a quick primer on PRNGs so we can show and tell some real PRNGs, then beat them up. So, okay, what is a pseudorandom number generator? It's just an algorithm for transforming numbers into numbers. It's deterministic, it's software realized in the cases we're talking about, completely deterministic. It has a number inside of it, an internal state, and it transforms it to another state, and pseudorandom numbers come out and the application consumes them. They're usually written for speed and simplicity. Like you can imagine they're being used in simulations or in circumstances where an application wants something that just looks unpredictable enough to the human eye, or something that achieves kind of a uniform distribution over some number space. These are not designed for security. Yeah, everybody knows this. It's the attacks are decades old, but apparently some developers enjoy doing it anyway. So I'm gonna task you with getting the message out that this should not be done. Don't use pseudorandom number generators in security-sensitive applications. If you're not sure, just don't use them at all. Use the cryptographically secure ones. But that is the extent of my public service announcement. That's all the mitigation and defense we're going to talk about. The rest of this presentation will be offensive. This is a general sketch of kind of what we conceptualize a PRNG being and how we can consider it being used. It's a component. It has an internal state which just kind of gets modified. It gets transformed as successive pseudorandom numbers are drawn out of it by the application. This application is just whatever code that uses a PRNG. It's not, it could be a kernel, it could be a web app, whatever. So this component, the PRNG, is initialized. It's seeded with some seed that maybe, for all we know, hard-coded in the application or might be derived from what we're labeling an entropy source. This is not necessarily cryptographic entropy. We're talking typically timestamps, process IDs, nothing really good. But we're talking about common cases, what you might expect to see in applications that are exhibiting pseudorandom behaviors. So we got our entropy, application takes it, transforms it into a seed. The seed is fed to the PRNG to initialize it, maybe once, maybe periodically, maybe kind of once per thread or something. And now, in PRNGs where the state is really no bigger than the seed, like say they're both 32 bits or something, then the seed is often just plugged in directly as the state. It might be tweaked a tiny bit. The other case would be where the state is significantly larger than the seed. And then the seed is run through some algorithm for deriving an initial state. For instance, .NET PRNG accepts a 32 or technically 31-bit seed, has like a 1700-bit internal state. So not every possible state is directly realized from a seed value. Oh yeah, this is important. So these numbers that come out of the PRNG go back into the application, and then they're processed. They're kind of massaged into, in the cases that we're examining, a smaller set of numbers. And that's this little dotted elbow there. And then finally we get some output from the application. This output is typically in symbolic, it's characters rather than numbers typically, just because there's a greater density of information, I guess, in characters than in, like, say a decimal representation of numbers. And it may be for human benefit too, like the application is emitting a generated password. Well, the password is going to be letters, numbers, etc. So there's this mapping from these output numbers into symbols that finally comes out of the application and reaches your eye when you're examining the application. Okay, wanted to emphasize the difference between a seed and a state. I think I already did that pretty well, but the seed just determines the initial state. Once the PRNG is initialized, it may run for some amount of, like an arbitrary number of runs. An arbitrary number of pseudorandom numbers might be drawn out of it. Now in cases where the state space is much larger than the seed space, then this means that not every state might be directly derived from a seed. This is important in a couple cases, so just something to keep in mind. So that is where the pseudorandom numbers come from, but where do they go? Where did they go? Here we are. So an application could, of course, be written to consume pseudorandom numbers in any conceivable manner. But the cases we're interested in, as we discussed, it draws out pseudorandom numbers one at a time and makes one symbol per pseudorandom number. Now that process of massaging, of processing a pseudorandom number into one of these output numbers, we're conceptualizing it as happening in one of two modes, and this is a pretty useful, pretty applicable, or excuse me, pretty accurate generalization. This typically happens in one of two ways, either modular, in that the output number has the modulo operator applied to it. It might be explicit using, of course, percent or bitwise and, or it might be implicit due to, say, integer truncation, like say it's cast to a byte. Well, that's an implicit modulo 256. The other mode would be this multiplicative mode, and usually what happens here is that the number that comes out is normalized. It becomes a float from 0 to inclusive to 1 exclusive, and then that number is going to be multiplied by whatever the application wants to expand that into the desired range. The modular mode, we've got a few different things going on here. The big rectangle is the raw pseudorandom number. Usually that's just the state, just pulled directly out of the PRNG and then fed back to the application. But sometimes there are a few transformations that happen. And of course, an important number here is the big modulus. That confines the entire range of pseudorandom numbers that might come out. So say, for this modulus, the numbers might range from 0 to modulus -1. This modulus also may be implicit, like 32, like 2 to the 32nd, if there's, say, an internal 32-bit state variable. Just due to truncation, it's confined to 2 to the 32nd. Or it might be explicit. Often in the explicit cases, it's either a power of 2 or some prime number. Like, they like Mersenne primes, like 2 to the 31st -1 especially. So then a few other things happen. Assuming that most of the parameters of the PRNG are powers of 2, people have noticed long ago that the least significant bits tend to have a short period. They tend to be fairly predictable and not especially useful for randomness. So they're often discarded. And that's what's going on here. You can imagine this 32-bit number coming out of the PRNG, or, okay, not quite coming out of the PRNG. Immediately before it leaves, they would divide it by, let's say, 2 to the 16 if they want to discard the 16 least significant bits. This might be a division, it might be a shift right 16, but either way, you get the idea. The least significant bits just get lost because they're deemed unsuitably periodic. That leaves this upper portion, the output portion, which may actually be confined further, what we're calling an output modulus. For instance, there's one PRNG that actually it drops the 16 least significant bits, and then it keeps the 15 least significant bits of that. So this part, this most significant bit gets lost, which would give us an output modulus of 2 to the 15, or 32,768. Now this limit here, we'll talk about that more in a little bit, but that's of critical importance. This is what the application is doing to the pseudorandom numbers that come out of the PRNG. It's applying, in this case, in this modular, this take from bottom mode, it's applying this limit as the operator to the operand to a modulo operator. And now say that limit shares some factors with this, the size of this output portion. Then some interesting things happen. We go over that in much greater detail in the white paper, so I'll refer to you to it again. But the point is that most often it's the least significant portion of this output part that's being kept, which contrasts completely with the multiplicative mode, this take from top mode, where again we've got the raw number, we discard some of it, might lose an additional part on the top, and then what remains is typically divided by rand max plus 1, like the number just greater than the greatest possible number of this, to give you that normalized float from 0 to inclusive to 1 exclusive. Once you have that float, then the multiplication by the limit to confine it to the range that the application is interested in. So this is, so the pseudorandom number is pretty well processed by this point. We have what we're calling an ordinal value. Like say they want numbers from, like numbers from 0 to 25. At this point, these ordinal values are ranging from 0 to 25. But again, the applications typically don't want to just emit raw numbers, they want to emit symbols. So there's this mapping, what we're calling an alphabet, from ordinal values. Again, say take the example of 0 to 25, might map to the symbols A through Z in the English alphabet. This mapping is the alphabet, and the size of that alphabet is the limit. So again, in the 0 to 25 example, 26 is the limit. And there are this is of critical importance. So if you tuned out, please tune back in, because this is going to come up a lot when he does his demo in just a second. Here's an example alphabet, and this illustrates a lot of the concepts that you'll run into when you're trying to attack an application. So there's what I'm calling, for lack of a better term, the principle of obviousness, where if the developer wants to spit out numbers, letters, then they're probably going to order them in A through Z order, just out of obviousness. Same with the numbers, typically 0 through 9, not always. Like looking at the keyboard, they run 1 through 9 and then 0. So what's to say that the alphabet is not going to be constructed where the numbers, the digits, are 1 through 9 and then a 0? Also, what determines the relative ordering of lowercase letters, capital letters, and numbers, and even symbols? Well, nothing really. There's no clear, obvious kind of what you're generally going to see case for how those letters and numbers should be ordered relative to each other. So in this case, we've got lowercase, capital, and then numbers. In other cases, we might have capital, then lowercase. We might have the numbers first. We might have them sandwiched in between. And then finally, the symbols. What's going to govern which symbols how they order the symbols? Maybe nothing. Like this is keyboard order right here, but they could go in an ASCII order or something. And then finally, this is a particularly pesky example, because down in the bottom we have duplicates. We have ampersand and then asterisk, both repeated. So while there's a definite mapping from ordinal values to symbols, there's not necessarily the reverse. Say if Prankster is given an asterisk in the sample with this alphabet, it's not going to know if that should be ordinal value 69 or 71. Now the PRNG is of course dealing all in numbers, so we need to deal in numbers to derive the internal state of the PRNG. So that is a condition we don't currently handle. It's certainly not beyond the realm of like practicality or possibility. We just don't handle it. But even if you give Prankster an alphabet that contains duplicate symbols, as long as your sample that you're feeding in, that you're trying to test, does not contain any symbol that's duplicated, it'll still work. So now I'm going to show off a few of the, the PRNGs that we examined and kind of where they fit into all of this. There are really two categories, and then there's a straggler or two. Linear congruential generators, I'm going to say LCGs from now on, are the most common. They're perhaps the most well understood, the simplest, and they're pretty effective. We got some array-based ones. They're kind of interesting, and then our others. So this looks a little hairy, a little mathy, but it's really simple. You got the state of your PRNG. It's just a number. It gets multiplied by some number. It gets another number added to it, and then taken modulo some modulus usually. Again, that could be implicit, like just 32-bit integer truncation. So just state times a number plus a number, get the new state. Now, that's what's going on inside the PRNG. What the application is going to do, or I guess what the PRNG might do before it returns the number, is apply that discard divisor and then that output modulus, and confine that to the numbers from 0 to rand max that are going to come out of the PRNG. So that's just the definition of the constants. That rand max macro or constant is in, I think, standardlib.h. It's historically 32,767, but it may be like 2 billion or more nowadays. It's just kind of varied in time with the size of the integer type. So here's a table of the PRNGs we examined, and they each kind of have something a little bit instructive. The MSVCRT, it's just kind of a good standard PRNG to cut your teeth on. Java is interesting because it maintains a 48-bit state, which is starting to get into that realm of impractical, not really feasible to brute force. It also operates in both the multiplicative and the modular mode, the take from top and take from bottom. Because the random class in Java, you can pass it the limit, and it will whittle down the pseudorandom numbers for you. Now, if you pass in a limit that's a power of 2, it uses the take from top mode. If it's not a power of 2, it uses take from bottom. The most interesting case, though, is when you pass in a number that contains factors that are powers of 2. I mean, we're talking even like an even limit, because 2 is a power of 2. Then it will still use a take from bottom mode, and some interesting things happen. We've implemented attacks that take advantage of that into Prankster, and we talk about it in the white paper. Just don't have time today. BSD libc, it's got this add-in to 0. It's kind of interesting, and then a prime modulus. VB script is it's a joke. They have a 24-bit internal state. I mean, you could brute force that even without any attacks, but we have attacks anyways. And VB script is, of course, also used in ASP and stuff. And then finally, we got the Microsoft SQL Server PRNG, which is also used by PHP, but only, I think, in their session ID generation. See Camcar's work for that. We reference it in the white paper. It uses 2 LCGs with slightly different parameters, like those moduli are slightly different. And the goal, I think, is to get this composite PRNG that has a period of both of them multiplied. It does some other slightly funny stuff, but anyways, that's beyond the point. Array-based. These are kind of fun, kind of uncool. They have a huge internal state. They keep this array internally of n, let's say 30, 50 integers, and these integers are all modulo m, which might be 2 to the 32nd, it might be roughly 2 to the 31st. But how they work is they keep this internal array, and then they take a number, they add or subtract the next number, and then store that and return it. And then after that arithmetic, they would rotate the array. But it's kind of inefficient to talk about rotating an entire array in memory every time, so instead they step indices through it. It accomplishes the same thing. These 2 indices are always a fixed separation apart. So these are the 3 most important parameters of these array-based PRNGs. The number of integers, the size of the array, the modulus, and then the separation. And those totally affect its behavior. So here's just a little summary. .NET, array of 55, they took it, I think, from Art of Computing or some old book, except they changed a few of the parameters and might have fat-fingered the separation. Like it was 31 in the book, they implemented it as 21. We haven't yet worked out if that actually affects, if that undermines the PRNG in any way. It probably impacts the period, but I mean, again, we're talking about a PRNG with like a 1700-bit internal state. So its period is still going to be gargantuan, even if it's a small fraction of the gargantuanness it could have been. glibc, type 3, the default RAND nowadays, also array-based, array of 31, separation. A couple interesting things is that it adds numbers, whereas .NET was subtracting them, and it adds an earlier number to a later number. Now this, there's a separation of 3 there, but because they did it that way, it's effectively a separation of 28, 31 minus 3. And another thing is it brings back the discard divisor. The least significant bit of each element is lost, is shifted away, it's hidden from us before they ever even return that number from the PRNG. Now the comments in their code, they say this creates a linear feedback shift register, which I'm not going to get into much. In those hidden bits, which, I mean, the bits are hidden, but their effects, the addition of them causes carry out sometimes that, was a little hairy at first, but we're actually able to parlay that into an extremely interesting attack. Well, one is we just don't have time to demo that today, and 2, we don't have the RAM. It requires about 24 gigabytes of RAM, our attack implementation, time-space thing. So we're not going to demo that, but it's also spelled out in the white paper. And then we got this pure basic PRNG. It's kind of weird. It's got 2 arrays of 17 elements each, and it does a little bit of bit rotation and then some swapping back and forth. And it's just trying to be weird, but I'm not going to worry about it right now. Really cool feature of these array-based PRNGs is that they can exhibit these recurrence relations. I mean, you can express, like you can succinctly mathematically express the PRNG as a recurrence relation, but this manifests when you start getting long strings of consecutive outputs. Like say the .NET case. Say you get like 60 outputs, more than the length of more than the size of the array. You'll start to see things like if you take the ith element of your output and subtract the I plus 21st element, then you'll get the I plus 55th element. And on, like you can, like any triplet you have like that, you'll get. Now some error does come in. Each time you make one of these predictions, there's a 50% chance that you'll be off by some fixed constant. Now that fixed constant tells you some useful information. Well, for one, if you see one of these relations start to manifest, that tells you what PRNG you're up against. And if the constant that you see in that error can tell you about the size of the alphabet, the mode in which that PRNG is being used, the multiplicative or the modular, and it can also tell you about the arrangement of the symbols in the alphabet. All extremely useful information for making your attack much more practical. So yeah, these errors are caused by just various elements of hidden state, another thing we talk about in the white paper. But yeah, it can actually have its uses. Finally, we got this Google V8 PRNG. It's in their JavaScript engine, and they called it a multiply with carry algorithm. There's a math for it. We're not really going to get into it right now. And then Perl tends to, in the limited cases I looked at, just the Perl basic RAND uses the underlying platform's RAND, but then just always normalizes it. Like it divides it by RAND max plus 1 to make it a float. All right, so now we've all been waiting for is actually attacking stuff. We got a four-step plan to help you attack pseudorandomness in these applications. Step 1, find an application. Find some pseudorandom behavior to attack in it. In the screenshot, we're getting like a URL that contains some kind of pseudorandom looking code. So step 2 is collect samples. Like here we have one sample, well we need more samples. The idea, the goal is to collect enough samples that you've seen every symbol that the application can throw at you. Like, in other words, you want to see every symbol that can turn up in its alphabet. After that, collect some more samples. Eventually, biases might start to emerge. Now this might happen quickly, like if you see one symbol that, and use proper statistical stuff, which I'm not qualified to get into now, but if a statistically significant bias starts to emerge that, say, a symbol is showing up twice as often as another symbol, then maybe that symbol turns up twice in the alphabet, like in the example we saw earlier. That's really important. For more samples, if you're at liberty to collect like hundreds, thousands, millions of samples, then subtler biases might start to emerge. Like if you find a symbol or a set of symbols that turns up 1/32,000th as often as other symbols, that tells you potentially what random number generator is being used. Like for instance, the Microsoft C runtime, because it's got its RandMax of 32767, so that will cause biases to start to emerge relatively frequently in many conditions, or relatively rapidly, I mean. So if you're able, start to collect samples, look for these biases, and that can tell you, again, what mode is being used. Like because the modular mode, the biased samples tend to cluster, or they're all at the beginning of the alphabet. Whereas in the multiplicative mode, they're kind of dispersed throughout the alphabet at even intervals due to rounding. Now that can also kind of hint at the order of the symbols in the alphabet, which is of supreme importance. Okay, so step 1, find something to attack. Step 2, collect samples. Step 3 is where it gets good. This is what Prankster's made for. If you have a PRNG, and you might be able to guess it from context, like if you're attacking a page that's .jsp, maybe it's Java's PRNG. Of course, maybe it's not. There's no harm in just trying multiple PRNGs if one's not hitting. But when you have the PRNG, when you have a guess at the alphabet, and you might have to again try multiple, kind of rearrange some things, and of course you have a sample, like in the previous slide, that sample that was in the URL. When you have these 3 things, then feed it to Prankster, and if all goes well, it'll give you back a seed that you can put into that PRNG to produce that sample, given that alphabet, of course. Now this doesn't work for all PRNGs currently because, like say, the PRNGs where the state is huge, there may not be one seed that produces that output. There may be a seed, but also a position in the pseudorandom stream, if you want to think about it that way. Like, imagine the PRNG was seeded, and then it was run for a while, and then it produced the output you got. If the state is way bigger than the seed, then we don't currently have a succinct way to express that. So the PRNGs we're talking about is where the seed is comparable to the internal state, like Java, Microsoft C runtime, etc. And so if all goes well, then on step 3 here, Prankster will spit out a seed, and then you're good. If your job is just to write a report and say, don't use insecure PRNGs, then write, don't use insecure PRNGs, and you're done. But in some hypothetical universe where clients don't believe that something's an issue until you exploit it, then we move on to step 4. So you have the seed, and you got some output, but we got to assume that other people are using this application and getting output too. And wouldn't it be cool if you could predict the output that they're seeing? Well, if you have the seed, you have this internal state of the PRNG, well, you can. Prankster will let you run the PRNG forward and backward to predict past and future output. Also, if you have that seed, you might learn something about the entropy that was used to make it. Like you might get the system time, which doesn't sound too exciting until you consider that it might be a local time. And if you compare that with universal time, maybe you learn the system's time zone. Could be cool. Say a pointer, like an address, was used to seed the PRNG. Well, you might learn something about its ASLR state. I don't know, there could be cool information in getting that entropy. So that's our 4-step summary of our methodology. Find something to attack, get some samples, recover the seed from Prankster, and then exploit it. And then step 6 is profit. So the tool we're calling Prankster. Why did we write this tool? Why are we all here today? Well, it's because, no, I don't think anybody's done this. I don't think anybody's implemented this before. There's been a lot of research attacking PRNGs, but I think they've typically focused on open source applications, like last year's talk, which was awesome, by the way. Please go check it out. Argyros, I think, was the presenter. But they did open source PHP apps, and they tend to focus on teasing out the seed, like getting the process ID back, or getting the system time, or whatever. We're looking at it from the opposite end, from the business end, the output that it's emitting only. So that's really friendly for black box attacking. That's why. And the what is these three functions, basically. So implicit in all these is you have to specify a PRNG. It won't try multiple PRNGs in the current implementation, like it can't, just that it doesn't. And there's no meta PRNG that it will figure out the parameters for you. So given a PRNG, a sample of output, and then your guess at an alphabet, feed that to Prankster, and if you're lucky, you'll recover a seed. These other functions are kind of for convenience. If you have a PRNG, a seed, and an alphabet, you could generate the output given that seed. That's just a convenient way to do the forward or reverse prediction. Or if you really need to predict into the distant past or future, then we have this third function, which is for seeking the PRNG. Not all PRNGs can be run backwards just because of their properties, and not all can be seeked or sought, but many can, and so we provide that functionality. This is its report card. So I like to call it Java just because, I mean, you know, there's for better or worse, there's a lot of Java out there. 48-bit state, we did the math, and it was looking like on our test system it would take about 96 days to brute force the full 48-bit state space if we, in a naive brute force. But we implemented attacks into Prankster that, given enough output, it can run in minutes to seconds. So it becomes a lot more practical. The same kind of applies for the others. If you're looking at V8 and kind of scratching your head, the V8 has a full 64-bit state, but 32 of those bits are negligible. I mean, they might come into play in 1 every 1,000 outputs or something. So we just don't even bother with them. And to be fair, somebody else's like a full naive brute force implementation might also not bother with them. So if this 20,000 years number looks a little daunting, even a naive brute force of just that 32 of the 64 bits of state would still take a number of minutes, and we've got it to under a second in the Prankster implementation. So that's enough out of me. Let's go to Gabriel for a demonstration.
Good question.
Do we want to take?
I guess you were using during the whole benchmark, you were assuming that all the outputs were from the PRNG using the same seed. It wasn't being received between one sample and the next.
Yeah, absolutely. The question is we weren't assuming that it's being reseeded, and yeah, this test run a run of Prankster, it's just trying to find all the seeds that could produce one piece of output. It's not trying to produce any other output. So the reseeding that might go on in the application is kind of irrelevant at that point. We'll try and, if the demo doesn't answer your questions, and this should be very illuminating, but if it doesn't, feel free to take them at the end.
Okay, demo time. Live demos are usually fun, except when you're presenting, and it involves randomness. So hopefully nothing random or pseudo-random occurs during this demonstration. So yeah, we're gonna show how to use Prankster pretty much. So say nowadays you usually have multiple accounts online, right? And of course you have a unique password to each one of them. So it's kind of easy to forget your password. And let's say our guy here, John Silence, he forgot his password. So usually website will present this option to recover your password. So let's see if John Silence can recover his password. Okay, we should have an email with some instruction, oh, there we go, on how to reset our password. So some instruction, blah, blah, blah. And we can see that there is a interesting link right here. Let me see if I can zoom in. Yep, there we go. So that looks kind of interesting. There's the John Silence email address, but there's also this code that looks kind of random to me, right? Some capital, lowercase letters, numbers. So it doesn't look like a hash or base64 encoding or anything like that, but we may want to get more samples just to make sure what are we dealing with. So let's get another email. There we go. And yep, different code. Yeah, complete different code, but still we got uppercase, lowercase, and numbers. So we may use Prancer to attack, test the security of this website. So what Prancer can do for us. Prancer is an open source tool. You may already have it in your CDs or you can download it later. It's open source, it's written in C#, so you can compile it for .NET Framework or also for Mono, which is supported at Mac OS and Linux, of course, and some other platforms. So that's pretty cool about Prancer too. So let's see, what kind of options we have here. This is really helpful. I'm glad you included this option in the tool. We're interested in this two first option. The R stands for recover. So we can use Prancer to recover the seed that was used to generate the output or the code or the token, in this case of this email to reset the password. And then we can also use the option G, which is used to generate future or past output based on the seed that we can recover for the first step. So as we can see, we're gonna need the PRNG and also the alphabet to figure out the next code. So let's do that. PRNG. Back in the day, you can usually take a look at the website, and from the web page, you can tell whether it was Java, for example, if you got a JSP extension, or PHP or ASP. But nowadays, we love URL that are friendly to the user. So usually, you don't get extensions on your web pages. So we can do that in that case. Sometimes you can see like powered by Joomla, super powerful. And then you can say, okay, it's PHP or WordPress and PHP again. Sometimes you can take a look at the source code of the website and you can find something there. Yeah, in this case, I don't think, just a hunch, I don't think we can find anything here. So let's see if we can actually grab the banner for this website. Let's do that. Or at least try to do that right now. Yep. So okay, there we go. Let me see if I can find the headers. Okay, here we go. No server banner, but hey, check this out. Powered by Express. Now, if you go and Google that, will realize that Express is a web framework for Node.js, and Node.js happens to use Google B8 PRNG, JavaScript engine, Google B8. So, yep, sure enough, it's probably PRNG B8. So we got our PRNG. We now need to figure out the alphabet. Yeah, right there. So what else can we get from this? We should probably collect more samples, although it looks like we're facing, again, uppercase, lowercase letters, and then digits. So, but let's get a few more codes. Yep, there we go. 8 characters, numbers, letters again. Just one more, just in case. Yeah, pretty much the same. So, yeah, we can tell that we're facing the alphabet with numbers and upper and lowercase letters. So let's see, I'm gonna actually use this Python script. Super simple. You can actually do that in command line, but I'm gonna use this guy to generate the alphabet for us. So there we go, digits and letters. So okay, I'm gonna take a code from the email. I'm gonna use the second to the last code. That way we can generate the next one and make sure that Prankster is working properly. So I'm gonna copy this code and paste it here. So then we're gonna go Prankster, the option R for recover. Then we need the PRNG. In this case, it's PRNG B8. And now we need the alphabet. So let me copy this guy real quick. And there we go. So if we're lucky enough, if I hit enter, then we should have our seed. Let's see. Oh, yeah, live demos. But something's wrong here. Maybe the PRNG is not correct, but no, Express, Node.js, Google B8, that makes sense. So maybe the alphabet is wrong. Maybe the order of the alphabet is not the right one, or maybe they skipped some characters. I don't know. So let's try something else. I'm gonna actually clear this real quick, because sometimes Linux terminal is not very friendly. I'm gonna switch these capital letters to the beginning of the alphabet and see if that works. I'm gonna paste it right here. If that doesn't work, then maybe we can switch the digits to the final part of the alphabet, whatnot. Oh, there we go. We got the seed. So that's pretty awesome. That was less than a second, I guess. And now we can use this seed to actually generate more output for this application. So let's do that. Actually, I'm gonna reuse that again because we're gonna need the alphabet. I'm gonna take this part off real quick. So instead of the option R, we're gonna use the option G for generate. And then we also need the PRNG, we still need the alphabet, and finally we need the seed that we just recovered from the previous step. And something else, we need to tell Prankster how many outputs we want to get from it. We saw that the codes are 8 characters length, so we're gonna actually recover the current code and see how that works. Okay, there we go. Let's see if that matches. Is this maximized? I guess so, but yeah, for you, blah, blah, blah. Yeah, pretty accurate. So that's kind of cool, but we're interested in the next output. So we're gonna ask Prankster to generate actually 16 characters, and let's see how that works. There we go. So this was the original code we gave to Prankster, and now we got another 8 characters. So let's see if that matches. Kind of. Chucks. There we go. Kind of. You can see that something is not good with this. Okay, never mind. So something's wrong here. We're missing one character, capital C at the end, and that's not good. And we also have this capital O here that doesn't correspond to the code we got in the email. So something's wrong here. Yeah, I guess the application is actually discarding one letter. It's discarding one output. So we're gonna need to generate more so we can get that capital C, and then we can also discard that capital O or capital O from this. So let's do that again. Instead of 16, we're gonna say 17, and fair enough, now we got another 8 characters, and that matches the code we got in the email. Cool, pretty cool. So what can we do with this? Well, maybe generate someone else's, reset someone else's password. Oh, the admin email address. That's kind of cool. We can probably help him recover his password. So we're gonna do that right now. Now, usually if the application, the website in this case, is very busy, there are a lot of users with common passwords, so you want to make sure that you're using the latest output as possible. In this case, I got a sense that nobody's using this website right now, so we're safe using the same seed we just recovered, okay? So I'm gonna use the administrator email address, and okay, now I guess we can generate another 8 characters, but remember the application is describing 1, so we want actually 26. So this last 8, 3, 6, 8, is that correct? Yep. Or no? There we go. Jay? Thank you, Guy. I'm not good with numbers. Okay, I'm gonna copy this to my clipboard, and I'm gonna just click on this link instead of copy paste it. So we actually, it works for John Silence. That's pretty cool. We want to change this email address. I'm gonna use the administrator email address, and now we want to use the code we just recovered. I'm gonna paste. So that should work, right? I'm gonna hit enter and see if that, okay, pretty cool. It works, so let's reset this password. I'm gonna use an easy one. Thank you, that's pretty cool. And I guess we can now log in and awesome, we got access to the administration panel. Thank you. So, yep, that's how easy it is to use Prancer. Hopefully you will enjoy it. And now, I guess we have some times for questions.
First, sir, I wanted to, just in case the demo didn't illustrate, I finally understood, I think, the spirit of your question. And yeah, Prancer is an offline tool. Was that closer to what you were getting at?
You input the seed into the PRNG, and then you start generating random numbers, and you start using them. And that's what he did. He found the seed, and then he started generating the stream. But if between one invocation and the next, I reseed the PRNG.
Yeah, definitely. There are practical complications that you'll just have to encounter and address, such as, are there multiple threads? And do each of these threads have their own instance of the PRNG? And does it get reseeded periodically? How many get discarded like he showed? You know, there will be quirks and nuances, but in general, I think this is pretty generally applicable. Do you have a follow-up on that?
Follow-up. You actually tested against any implementation. I'm not asking names.
I'm sorry. The question. Thanks. Yeah, the question was if we've actually tested against any, I guess, real-world applications and such. We don't have any results to disclose right now. I'll just put it that way. And sir in the back. What's the question?
How much have you made on slot machines?
You know, I was waiting until after the talk to mention slot machines because, you know, I don't want to upset our hosts. But I heard that BlackHat's not going to be here next year anyway. So let's talk. No, I'm just kidding. Actually, slot machines are regulated by the Nevada, I think, Gaming Board, and they have to use cryptographically secure RNGs. So yeah, I don't think you're going to go downstairs and make a mint with this, but could be wrong. Yes, sir.
What was the method that you used in order to not access brute force all the 48 bits?
Okay, thanks. That's what I really wanted to talk about today. Yeah, okay, thanks. And that would be, what method do we use to reduce the brute force? Well, we pair off large amounts of the space through a variety of means. There's what we call a subgenerator attack, which is if the properties of the PRNG are such and the limit contains a factor of 2 or power of 2, then it has that least significant portion that has the low period the reason for the discard divisor. But the discard divisor is not enough. I mean, that was not intended as robustness against adversaries, and we're being adversarial. So there are sub-generators you can use to brute force the low part and then brute force the high part separately. So instead of brute forcing 2 to the 48, you brute force 2 to the 17 plus 2 to the 32nd or something, or 31st.
All the attacks are described in the white paper, so you should definitely check it out.
There are other attacks like partially fixing the state. We're in these, sorry, I just really like talking about this stuff. This is fun. Where, say, especially if it's operating in a multiplicative mode, then typically what happens is the PRNG transforms its state and then outputs stat. And so if you see an output that is really at the low end of the alphabet, then you know that the state of the PRNG after that is in the really low part of the state space. It came out to some float that was like 0.0 something or whatever. So you can fix that part of the state and then brute force the next part of the state. And then once you get the next, like a smaller sliver, like say for a limit of 26, you brute force only 1/26th of the whole space. And then you can reverse the PRNG one to get back the seed that produces the full output. And on and on. There are a bunch of different little things because each of these PRNGs have their own kind of, idiosyncrasies. Hope that helps. What else? Yes, sir.
Where's your white paper?
I was hoping I'd be able to tell you all that before I got up here. If you have a CD in your bag, it would be on there. If not, hopefully they put it on the website. If not, we're definitely going to put it on the website as soon as we get home from BlackHat, if not sooner. So stay tuned. Yes, sir.
Did you try to guess any of the open source random number generators? Pseudorandom number generators?
The question is if we tried against any of the open source PRNGs, and the answer is, for varying degrees of open source, like say .NET. Well, Microsoft has released .NET as semi-open source. Their CLI, their Rotor implementation, and so you can get the source for that, and that
Google
was
V8 as well.
Oh yeah, absolutely. Google V8. Others we didn't try, like PHP. Like we didn't really look at Mersenne Twister or anything, which has is really popular. The fellows last year looked at Mersenne Twister, if you're interested. So we've looked at some of them. We stayed away from the ones that are supposed to be more cryptographically secure just because we needed a place to start. And actually, even at RSA earlier this year, there was some analysis of other open source, more cryptographically secure PRNGs. So we do reference that also in the white paper. Others?
Cool.
Thanks. Y'all been a great audience. Thanks for showing up.